Do we have any questions on anything from last time? Types of chemical reactions? No? Okay, before we get started on today's topic, the last topic really, let's you guys start on the signature assignment for the e-portfolio. Anybody look at it? Okay. I gave you this a few times ago, but I never talked about it. I meant to talk about it, but did not. I gave it to you. And then I meant to talk about it last time. So here we go. So this is pretty much a final review. Now, don't just limit your review to this, but this kind of goes through everything we've done and kind of reiterates what we've learned in this class. Are we good? I tried to write it a little bit more clear than last semester. A lot of students were saying, what is this even asking? So I try to make it more clear. I want to help you with this, and I'm not going to do it for you. The hardest part is question 8. Well, I just shouldn't say the hardest, the longest part. Okay. So there's a bulleted list of things you got to do, right? So you have to do it comparing two different compounds. And if you read, it'll tell you which compounds. And just make a table. Say, okay, with 3 columns or whatever. One column, what is this asking, right? This is the first point. Then you say it for the first compound and the second compound. And then take as much room as you need. Next bullet. Don't try to cram everything in. It won't be complete. So just do one at a time. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 things you got to do. You'll get there. It's not too bad. Just going to take a little bit of time. Okay? And so I just want to, on the very first page, it has a bulleted list of tasks that you need to do. Okay? Read that first. For example, I'll just tell you one of them. There's a lot of students that don't want to do this. I don't know why, but okay. You've got to have a blank sheet of paper that you write these on. And you're going to label them number 1 through 8. And don't just label them 1 through 8 and then do it, right? Do 1. Take all the room that you need. And some of you have been doing the Feynman notes and some of you haven't. And that's your choice, but it's just a technique to help you to know that you understand this, or give it to somebody else and help them understand it, right? So if you can write it in such a way that someone will be able to follow what you're doing and understand it. That's it. Show your work, basically, right? If it's hard for me to follow, I'll likely dock you down because I can't see what you're doing. But if you have it written out really well, showing all the steps, show all your units, everything. Dimensional analysis, that's the big thing in this class, right? Any questions on this project or this signature assignment? Okay, once you've done with that, then you write a reflection of this course. Right? And you post both of those, the reflection and this assignment, on your e-portfolio assignment or e-portfolio website that you made at the first of the semester, and then you'll submit a link. That's it. Any questions? Okay. Let's talk about the remainder of the semester because we're just about done. Crazy, right? So tonight we will learn the last of the material for this class. And next time, so on Thursday, we could either do a review for Unit 4, or we could have a session where we go over this. So for that to happen, you guys got to come prepared for both cases, right? Come prepared, do the Unit 4 test review, and come with questions if we're going to do a review of Unit 4, right? If we want to go over this e-portfolio assignment, then start working on it. Come with questions. If your question says, hey, how do we do number 1? Hey, how do we do number 2? Number 3, number 4, number 5, number 6, number 7, number 8, I don't want to help you. Okay? I want you to put in the time. See if you can get it. Now, if you say, okay, on number 1, where it says, yeah, that's what I'm looking for. Those types of questions. I mean, I can help you with all of them. That's okay. But have specific questions to where we can start with something. Okay? What are you feeling? Is that a good plan? And then next Tuesday, a week from today, we'll do a final review of everything. I'll do it similarly like how I did with the midterm. I had the midterm test in front of me, and I says, this is what you need to know. Was that helpful to you guys? That's what I will do. I won't give you the exact questions, but I'll say this is what you need to know from the test. Okay? So I feel like that'll be a good use of your time on next Tuesday. And then the following Thursday will be the final exam. In class on paper. Unless you're online, then you take it at the testing center, right? And you could take it in here, that's fine. And sorry, I got your message a little late. Any questions, comments on the rest of the schedule for the rest of the semester?
So this following Tuesday, yes. So Thursday is the possibility of Unit 4 and that.
Uh-huh.
Right? What is Tuesday?
Tuesday's a final test review.
Final test review.
Final exam review.
And then
Yep. Anything else? Okay. Any other questions before we get started on today's topic? Okay. If you do not do this signature assignment, e-portfolio assignment, your grade will go down close to 10%, probably like 9%, if you don't do it, okay? So do it. Now, I have had students in the past that go, oh, I hate the e-portfolio assignment. It's a general course. It's required by the school. So we tried. It's better than the ones I've done in the past because it's actually chemistry stuff. It might not be realistic, but it's okay. It's pretty cool. Okay. All right, let's get started. All right, so today's topic is chemical formulas. We talked about chemical formulas already. We talked about writing chemical formulas, right? Today we're going to be a little bit more specific. How did we come to say water is H2O? How do we know that? How do we know salt is sodium chloride NaCl? How do we know that? Okay, so I can't really show you in this setting. If we have a mass spectrometer or an infrared spectrometer, we can figure these things out. But when we use that, it doesn't come out, this is water, H2O. It doesn't say that. It kind of gives us some graphs that look something like this. And that's a bad drawing, but something like that, and we say, okay, since the frequency is right here, we can say that's a carbon, right? Or something like that, right? In the mass spectroscopy, we can say, okay, what percentage is what, and all that. And if you want to learn how to use that stuff, take organic chemistry. Anybody take organic chemistry? Okay. But we're not going to do that in this class. We'll just show you what they do after they get this information, get this data. Okay? So before we get started on that, let's talk about something real simple. You guys okay with percentages? Can you do percentages? We've done a few in here already. Well, how do you do percentage? What's the general percentage? How do you do it?
Divide by 100.
Almost.
Multiply by 100.
We do multiply by 100. What do we multiply by 100?
What we got versus the total?
That's
Or-
it.
Yeah.
What we're interested in, so percentages are what we're interested in. I'll just say interest. Over, it's always over the total. Always. Okay, so that puts it in a fraction form, and if you type that in your calculator, it gives you a decimal. But that decimal doesn't mean anything. Well, kind of does, but if we times by 100%, it converts the decimal into a percentage, right? And so we can kind of say, okay, if I say 80% this and 20% that, I kind of know how much I have of each one, respectively, right? Or relatively, okay? So that's percentages. Done. The percentage we're going to do today is called percent composition. Who can tell me what composition means?
What the things are made of?
That's it. What it's made of, what it's composed of, right? What it's made of. And we know percent, this is our percentage, right? Okay. So if we have, for example, H2O. When I say what's the percent composition, we want to know what percent is hydrogen and what percent is oxygen of water. And whenever we talk about percent composition, it's always by mass. Okay. Hence, that's why we use the mass spectroscopy, right? And again, I don't have all that stuff here to show you how to do that, and that's not this class, okay? But let's see if we can find the percent composition from what we know. If we're going to find percent, then we need to know what we're interested in and what the total is. And then we could times by 100, right? So if we're interested in percent hydrogen, well, let's find out what the total is first. The total what? Total mass. For how much water, right? You got to know how much water before you find the mass of it. So what have we been talking about in this class? The amount. How much? 1 mole, right? We can figure that stuff out for 1 mole. Do we have a scale that measures how many moles? No. All this is to help us to figure out stuff, right? Make good predictions. All right, so let's find the total mass for 1 mole of water. Who can tell me what it is? 18. We've done this several times, right? Do you have to memorize 18? No, it's easy. Just count it. You got hydrogen has a mass of 1, but there's 2 of them, and oxygen has a mass of 16. So that's a total of 18 grams per mole, right? So I have 18 grams for 1 mole of water. So that's the total, right? So if we want to find the percent hydrogen, then that goes on the bottom, 18 grams, right? Well, what's the mass of hydrogen in 1 mole of water? 2. How'd you get 2, Vid?
It's 2.
But how?
Two
Oh, right here. We just figured this out, right? 2 grams out of the 18 grams is hydrogen. And then we got to times that by 100% to convert a decimal into percentage, right? And we can see grams goes away. So it leaves us unitless almost. Our unit is percentage, right? And so what is that? 2 divided 18 is 11 point, or then times by 100, right? 11.1111. We'll just say 11.1%. Are we good? Okay. Let's set it up for oxygen. What goes on top? 16. Out of 1 mole of water.
Do like 100 minus 11.
You could do that. Yes, you could. Yes, you could. Perfect. You guys understand what Vitter says? Since we have two elements here, if 11.1% is hydrogen, then to find oxygen is 100 subtract 11.1. Right? Which is 88.9%.
If you round it up, yes.
Okay. Well, let's see if that's what we get. And we're just going to do this old-fashioned way, right? So 16 grams. Come on. 16 grams for every 18 grams. So 16 grams of oxygen and 18 grams of water times by 100. Grams goes away, leaving us with, should be 88.9% if we did our math right. Good? Does that make sense to everybody? If percentages are easy, then this is easy. If they're not, well, let me know what I can do to get you there. And again, you add these and they should add up to 100%. If they don't, something's wrong, right? So there's a couple of ways you can check it, right? So if you like doing it the way Veer did, then check it this way, right? Just to make sure it's right. Are we good? All right, let's do another example. What's the percent composition of ammonia, NH3? Do you want to do this by yourself?
Yeah.
Oh, good. So go ahead and try that, and then we will discuss this. So we're doing this one on the board. You understand it?
No.
Or did you miss? Okay. Oh, okay. I am updated on posting the videos. Sorry it took me a while. I was out of town. But I will try to post this tonight. That way you can... I will post it tonight. Okay, who's got this? What percent of ammonia is nitrogen?
82.4.
82.4%. We all good with that? And that gives us 17.6% hydrogen. Are we good?
Yes.
So just by looking at it, for example, I mean, you'd say, okay, this is mostly hydrogen because there's 3 out of 4 atoms, right? But if we're talking about mass, nitrogen is more massive, right? So you got to do it with molar mass. Are we good? And of course, these add up to 100, so we did it right. Good? You want to try another one, or is this easy? Too easy? One more? Okay. Let's do a little bit harder of one. Let's do sucrose, table sugar, C12H22O11. Now we got 3 of them. We can't just subtract from 100 on, well, we can at the very end, right? We have to at least do 2 of them. So let's find in fact, ladies and gents, let's do the molar mass together. And if you show your work, it saves you time in the end. What's the molar mass of carbon?
142.
12, but there's 12 of them, right? So I'm just showing my work here. What's the molar mass of hydrogen? 1, but there's 22 of them, right? And the molar mass of oxygen is 16, but there's 11 of them. So we multiply those and get 144, like Vera said, 22 for hydrogen and 176 for oxygen, if we do our math, right? And I add these together and I get
342.
342 grams per mole, right? All right. Well, we have the numbers right here. Can we just divide all of them by 342?
Yeah.
Right? And so carbon, and then multiply by 100 to all of them. And that's it. So carbon should be 42.1%. Hydrogen should be 6.4%. And oxygen should be 51.5%. Add these together, do they add up to 100? They do. So show your work just from the, right from the the molar mass. And it saves time-ish, right? We're good? All right, that's cool. So a compound, so if we use a mass spectrometer, it might give us the percent composition, right? Percent of each element. We might have to use the IR spectroscopy to figure out what elements there are. Well, and again, we're not going to do that here. So from there, we got to figure out what's the chemical formula of this, right? So the next thing we're going to do is empirical formula. An empirical formula is the chemical formula with the lowest whole number ratio with the lowest whole number ratio of elements. What does that sound like? Do you remember?
Multiplication.
Not quite. Does it sound like the chemical formula for an ionic compound has to be written in lowest whole number ratio? We got to simplify ionic compounds, right? So when we write the empirical formula for an ionic compound is the same as the chemical formula, right? Or we call it molecular formula. But for covalent compounds, it's not necessarily the same. Sometimes it might be. So here's, and we use this to figure out what the substance is, okay? So step one, we convert the mass. So if we're given mass or percent composition, I'll show you how to do that in a minute. So we convert mass of each. Let me just do a problem, because I don't think these steps will be very useful without an example. So let's just do that example. Let's say we have 1.71 grams of our substance is carbon, and 0.287 grams of our substance is hydrogen. Okay? So we know it's a carbon-hydrogen compound, right? But the only problem is we don't know what numbers go right here, right? Now we might be able to figure out with ratios to figure out what the exact number is, but it might be kind of messy and icky and take real long and think, there's got to be a better way. So I'm going to show you that better way, because there is, okay? So all we're doing here is proportions and ratios. That's it, okay? No other math than that. So what do these numbers represent in a chemical formula? Who can tell me? Number of atoms of that element, right? Number of atoms, okay? So for water, for example, we have 2 atoms of hydrogen for every 1 atom of oxygen, right? But could it also mean something else? Is there the same number of particles for every what? In any substance. 6.022 times 10 to the 23 atoms is the same as what? 1 mole of that substance, right? So if we say, okay, there's 2 moles of hydrogen for every 1 mole of oxygen. Is that true? It is, because the number of particles is the same in 1 mole. So we can figure out how many atoms that is. Well, what do you think? A little bit of atoms or a lot of bit of atoms? Starts with an L. Sorry.
A lot of atoms?
There's a lot. There's trillions of them, right? If we have 1.71 grams of carbon, we have trillions of carbon atoms. We're not going to be able to count these things, okay? And then we'd have to use 6.022 times 10 to the 23. Who wants to do that? Is that fun? No, right? We know the ratio, 1 mole for every 6.022 times 10 to the 23. And that's for every element. So let's just convert this to moles. And we know how to do that, right? Convert this to moles, we have 12 grams of carbon for every 1 mole of carbon, right? And we learned this several times ago, right? And hopefully we got good at this, practiced it, and got real good at it. Because this is what we do in chemistry, okay? So we do 1.71, and we divide by 12. What do we get?
Could you repeat that again?
Right here. I'm just doing the dimensional analysis here. 1.71 divided by 12 should get 0.143 moles of carbon. Yeah? We'll do the same thing down here. 1 gram of hydrogen for every 1 mole of hydrogen. I bet you guys can do this in your head. What is it? 0.287 moles of hydrogen, because it's just a 1-to-1, right? And if you guys use 1 mole for every 1.008, that's fine. You could do that too. And remember, I told you if you're going to round, then round smart, right? If you're not sure if you should round, then don't round at all, right? Same thing goes here. But when you do this step, when you convert it to moles here, don't round any shorter than to 3 decimal places. You can have more digits, that's fine. Just don't go any shorter than 3 decimal places. Because the more you round, the more error you're going to have, and they're going to think, okay, this doesn't sound right. So don't round that much here, okay? All right, so we have 0.143 moles of carbon. Oh, so we got the answer. C 0.143, H 0.287, right? Is that true? That's true, but we're not going to leave it that way. It doesn't make any sense. You can't have a fraction of an atom, right? So we want, the empirical formula is lowest whole number ratio. These are not whole numbers, right?
You can just divide them.
Divide,
So 1:2.
what should we divide this one by?
287.
0.287? What should we divide this one by?
0.143.
Will it make them whole numbers?
No.
That won't make them whole numbers.
1.
We want, okay, I'm going to come back to that. I like what we said there. She said 1, okay? We want to make this the lowest whole number ratio. What's the lowest whole number? Well, that's not 0, right? Because if it was 0, then it wouldn't. Then there'd be 0 of that, and that can't. That doesn't make any sense, right? So the lowest whole number is a 1. So which one are we going to make be 1?
C1.
This one right here. Why? Because that's the smallest amount, right? How do we make that a 1? By dividing by? What do we divide by?
Total. 287.
0.143 divided by 0.287. Is that going to make it 1?
Yeah, 1:2.
That's not going to make it 1.
By
By itself. Divide it by itself will make it 1. Does that make sense? And we're going to pick the smallest amount to make it 1. Because that's the lowest number. We want that to be the lowest whole number is 1.
Cancel each other and 1:2.
You're right. You're right. So we're going to divide both sides by 0.143. I said both sides. I mean both elements, right? Why should we do both of them?
That I'm thinking is like cancel each other and
Yeah. You're right. But I'm trying to help everybody understand. It's not just people who think like Veer. And you're right, Veer. You're a great thinker. You're right. But do you understand why we divide both of them by 0.143?
You can't just do it to 1, right?
Yeah, the ratio has to be, like Veer says, the ratio has to be 0.143 to 0.27 or 287. Has to be that. That's what it has to be. Okay, so we're going to multiply both of them by the same thing to get these whole numbers, right? So this is probably what Veer is doing in his head. Multiply by 1 over 0.143 over 1 over 0.143. This is a value of 1, right? We didn't change its value. It still has a ratio of that. We're good, right? So if we divide this by it, it converts into 1. And then we divide this by 0.143. And what's it going to be? So we have a 1 to what ratio? 2. 2.287 divided by 0.143 is 2. So now we have a smallest whole number ratio. Carbon's going to be 1, hydrogen's going to be 2. We don't write the 1, so we just write CH2. Now ask yourself, does that make sense? Can you repeat that? Question.
I don't know if I have a question, I just don't get it.
What part?
I don't know why you divide it by that, I guess.
Okay. So if we go to the definition of empirical formula, this is what we're trying to find. It's the lowest whole number ratio. And what's the lowest whole number?
So
1.
1 over 2.
So that's our answer. So the lowest whole number is a 1. So if we have this right here, which one of those is the lowest amount? 0.143 or 0.287? 0.143. So we want to convert that into a 1, because that's the lowest whole number. Now it might not be a 1, and I'll show you what to do in that case. But for the simple case, we want to make that into a 1. And how do we do it? We divide by itself. But so the ratio stays the same, we have to divide both of them by that same number, 0.143. Did that make more sense?
Yeah.
Anybody else? Okay. Let's do another one where it doesn't turn out to be a whole number, even if you make one of them 1. Because that'll happen. So let's do example 2. Let's say we have 5.31 grams of chlorine and 8.40 grams of oxygen in our compound. So again, it's going to be Cl, some number, to oxygen, some other number, right? So what's our first step? Convert it into moles. That's it. Convert it into moles. So what's the molar mass of chlorine? Look on our periodic table. 35.5. Don't ever guess. Always look, right? Always check. And I rounded this. If you didn't want to round, it's 35.45, right? Okay. To 1 mole. Did I get it right? Yes? Because I'm going by memory, because I don't have a periodic table right here. So you guys should make sure, check me, double check me. 1 mole of chlorine, right? And then do the same thing to oxygen. We've done this in several times. 16 grams of oxygen to 1 mole of oxygen. Grams goes away. Any questions so far?
I know this is going to sound like a dumb question.
It's
but-
not.
So we get the grams by,
I gave you the grams.
Oh, okay.
Yep. In this problem, I gave you the grams.
Mm.
In the next problem, I won't give you the grams.
Would it be a dumb
I'll-
question to ask how you, or?
I'll
next
show you.
question?
We'll get there.
Yeah.
Okay? I won't leave you hanging. Okay? All right, so we on this first one, we get 0.150 moles of chlorine. And on the second one, we get 0.525 moles of oxygen. Are we all with me? Any questions? Okay. So what are we going to divide both of them by? 0.150, right? The lowest one, the smallest one. 0.150 to both of them. That gives us a 1 for chlorine. And what does it give us for the next one? Somebody do that.
2:7.
Just a minute, you're going too fast. We want to make sure you're right. We're going to just So yeah, guys, if you understand numbers and ratios, yeah, you could probably get this with a lot less steps. But I'm showing this for the person that doesn't get numbers, okay? And this is the process of what we do it. So what's 0.525 divided by 0.150? Yeah, what is it? 3.5. Not a whole number. So can we just say it's CL103.5? Can we say that's our answer? No, we're still not there. So now what do we got to do?
Cell number 2.
Multiply everything by the smallest whole number we can to make them the smallest whole number ratio. That's it. Is the smallest whole number we can multiply, is it 1? No, because that's not going to change it. So we go to the next smallest. What is the next smallest? It's 2. So we times 3.5 by 2. Does that make it a whole number?
Yeah.
Yeah. So we're going to multiply this one by 2 and this one by 2. Whatever we do to the one, we do to the other. The same thing. So the ratio remains the same. And so we got to multiply everything by 2, and we get CL207. And you probably got that ages ago, right? No problem. Does that make sense to everybody? Do you want a list of steps? Would that help? Yes or no? Okay. If it doesn't help, don't write them. So step 1, steps for empirical formula. Step 1, convert into moles. Step 2 is to do what? Divide by the smallest amount of moles. Divide everything by the smallest amount of moles. And then step 3, if necessary, multiply by small whole number to make smallest whole number ratio. And ladies and gentlemen, if it would make sense to write it in different words so that you understand what to do, do it. Did I get this from a textbook? I didn't. I really didn't. This is coming from my brain. Okay? Is it similar to what you find in a textbook? Probably. Okay? But these are my words. What works the very best are using your words. Okay? But if you don't have any words, yeah, use mine. Are we good? All right. Let's say we're not given the mass, but we might be given the percent composition. Okay? So let's this is our example 3. So we have a composition of 27.29% carbon, 72.71% oxygen. So we have a carbon-oxygen compound, right? And we want to know, well, what's the empirical formula? And again, ladies and gents, this is just the first step to get where we're going. Finding the empirical formula. So we got to convert grams to moles. Can we convert percent to moles? We can't, right? So let's say I have a bucket of this carbon-oxygen compound. I have a bucket of it, right? And I grab a handful. What percent of that handful is carbon? 27.29%. And 72.71% is oxygen, right? What if Charlie comes, she has a smaller hand, what if she comes and grabs a handful? What percent is carbon? It's going to be the same, right? Let's say Incredible Hulk grabs a handful. It's huge. Same percentage, right? So does it matter how much we get? Then let's pick a number that's going to help us. What number of grams should we grab? Total number. Why 100?
Because percentages are by 100.
Yeah, that's it. Percentages, percent means percentum, per century, per 100, right? So let's pick 100 grams. We get 100 grams. Well, if we get 100 grams, how many grams is carbon? 27.29 grams. Done. So all we have to do really is just change the percent to grams and we're done. Does that make sense in everybody's mind? Why we can do that? Okay, good. So then we just do our steps. Convert to moles, divide by the smallest, multiply by a number if we have to. And that's it. Do you want to do this one on your own? Or are we done with these? Go ahead. As soon as somebody has the empirical formula, let me know. Give me the answer. Yeah, what'd you get?
One carbon and two.
So CO2, right? That's it. Who needs more time? So CO2 is what it is. Good? Now, sometimes we might have to multiply by 3 instead of 2. But how do we know? Start with the lowest, multiply by 2. If it doesn't make a whole number, then don't write those answers. Then multiply by 3, and so on until you get it, right?
Do you multiply what you got after 2, or do you just change the 2 to
After we divide by the smallest whole number, after we divide by the smallest amount of moles, and we don't get whole numbers, then we have to multiply by something, right?
Right.
But if they're whole numbers, like in this case, we don't have to multiply by anything. Does that make sense? All right. So, do we need another example, or are we okay? You tell me. If we want 10 more examples, I'll give you 10 more examples. But I don't want to waste your time. But more important than that, I don't want to leave you hanging. How are we feeling? We got one more topic to get down. We good with that? I do have 2 more examples if you want right here. Good? All right. So the empirical formula is great if it's an ionic compound, right? Then we can be done, because that's our formula. But if it's a covalent compound, we got to do something else. And we got to have more data to do this something else, but let's get it. Okay. Now we got to find the molecular formula. What's the molecular formula? It's the actual number of atoms of each element in the compound. So the molecular formula of water is H2O. The molecular formula of carbon dioxide is CO2, and so on, right? So this is the actual formula, written in simple words. Actual formula. So let me just give you an example and let's compare. Let's see if we can figure out how to do this. Let's take glucose. Glucose is C6H12O6. Now that's the molecular formula of glucose, right? MF for molecular formula. Can anybody tell me what the empirical formula for glucose is?
1, 2, 1.
Yeah, 1, 2, 1, CH2O. Divide everything by 6 and you get this, right?
Factor of 6.
Does that make sense? All right. So how are we going to go from here to here? Now, we could easily see, oh, you just multiply everything by 6, right? But what if we don't know what that is? We don't know what the multiplier is, right? We got to figure that out. So to do this, what's the relationship between the empirical formula and the molecular formula? Let's find the molar mass of the molecular formula. We've been doing this by mass. Let's continue to work with the mass. What's the molecular formula for glucose? C6H12O6. 6 times 12 is 72. 12 times 1 is 12. 6 times 16 is 96. That's a total of 180, right? So the molecular formula, molar mass, equals 180 grams per mole. What's the empirical formula molar mass? 30 grams per mole. Huh. Can we figure out the ratio from that? Or the multiplier, I should say, from that? 180 divide 30. That's 6. This is the multiplier. So we take this and we multiply by 6 and we will get that.
I thought we didn't have the.
We won't have it. I'm just showing you an example where we do have it. And let's show us how we find that multiplier. Because we do have to multiply the empirical formula by some whole number to get the molecular formula. Are we good?
So, as like you said, we don't know about the glucose first. So how do we know that it's...
Oh, good. I'm glad you asked that question. It says, how do we know how to find this number?
Yeah.
Yeah. The mass spectrometer will tell us that number. So that will be given to us.
Or just the number is given.
The molar mass will be given to us.
Not
Yep.
the
That's right.
Oh,
So we will find this and we'll be given that. That's it. Okay, let's do an example. So do you guys want an equation to find the multiplier? I basically showed it to you, right? Multiplier is the molar mass of the molecular formula. Let's write this down. So to find the multiplier equals the molecular formula, the molar mass of molecular formula divided by the molar mass of the empirical formula. That's it. Okay, just to save a little bit of time, I'm going to give you the empirical formula, all right? So let's say we find that the molar mass of our compound is 176 grams per mole. And we know the empirical formula is C3H4O3. What is the molecular formula? So the molecular formula is equal to the empirical formula multiplied by the multiplier, right?
1:2.
So what's the multiplier?
2.
So Vir got the multiplier is 2. To do that, find the molar mass of the empirical formula. With 12 times 3 is 36. 4 times 1 is 4. And 3 times 16 is 48. And that's a total of 88? 87? Depending on if we rounded wrong or not, right?
It's 88.
Do we need to go through that? We'll just type it in your calculator. And I just rounded. 12.01 I rounded to 12, right? 1.008 I rounded to 1. And 16 I rounded this way. That one's already 16. Or was it 15.99? I don't know. All right, so 176 divide 88, and that's 2, right? Or is it 2.00 something?
2.0.
Was it exactly 2? Okay. Okay, so our multiplier is 2. So we multiply everything by 2, and we get C6H8O6. Pretty straightforward. How are we feeling? I gave you a practice page that has answers on the back. So, plenty of practice for empirical formula and the molecular formula. And I gave you another sheet for the percent composition. You will have to do each one of those on the test and on the final. Okay? Make sure you can do those. Questions? Whoa, that's almost an hour early, guys. We're done. So if you want to do any more examples, we can. What are you feeling?
Let's just do it.
Okay, you want to do more?
Yeah.
Okay. If you want to do more, I'm going to stay and do more. If you got this and you got something better to do, where do you? No, you're not going to hurt my feelings, okay? You just go. If you want to go, I'm not going to hold you back, okay? But I will stay and do a little bit more examples. So let's do some examples that's on our worksheet.
Can I have a report for you, please?
Oh yeah, does anybody need the e-portfolio packet? Let's see. Yeah, I think I have some. Did you get one of these, Davis?
No, but I have it online.
Do you want this one?
Yeah, I'll take it.
Anybody else while I have it open?
Thank you.
right, did anybody want to do examples of percent composition? You tell me. We got 9 examples that we can do. Or do you want to just work on them? If you want to just sit and work on them, that's fine too. And I do have the answers posted on the modules. Okay. Okay, which one do you want to do, Charlie?
I guess,
A hard one, number 3?
yeah, number 3.
Yeah, number 3 looked
That's
tricky.
fine.
Okay. Because I just did easy ones, right? Okay. So let's do NH4 in parenthesis 2S. What's that called? Anybody tell me what that called? That compound is called?
Ammonium sulfide.
Ammonium sulfide. Perfect. Good. All right, so we got to find the percent composition. What's our first step?
Total.
Find the molar mass of this compound, right? So nitrogen, how many nitrogens are there? What's the molar mass of nitrogen?
It is 14. So
14.
There are 2.
And there's 2 of them. Good. Hydrogen has a molar mass of 1. And there are how many?
4 times 2?
Good, so 8. Perfect. Plus sulfur has a molar mass of 32, and there's only 1. So that's going to be 28 plus 8 is 36 plus 32 is 66? No, 36, 68 grams per mole. And again, that's the total, right? So for nitrogen, percent nitrogen, what are we going to do? How do we find the percent nitrogen?
We divide, let's see, so the 2 times 14 was 28, so we divide 28 by 68 and then times it by 100.
That's it. And that gives us what?
41.2 if you round it.
41.2%. Perfect. Okay, percent hydrogen is going to equal what? What do we do in our calculator?
Same thing, but with the 8 times 4.
8. 8 times 4 or just times 1?
8 times 1, excuse me.
Okay. Divided by what? Also 68. Total's always the total, right?
Yeah.
Times by 100, what do we get? 11.8%. And percent sulfur is going to be 32 divided 68, right? And we get that right from here. Times by 100, what do we get?
Uh, 47.1.
We rounded one of them a little bit off
Oh,
because if you add these together, what do we get? 100.1, right? It's like, oh, too much. So it's just a rounding error. That's fine, right? You got the idea.
but which one do we lower to make it correct? Or
That's a good question.
should we just leave it?
Good question. We could just do that.
We can just do what?
I just changed 47.1 to 47.0.
Oh,
Is it the right thing? I don't know. So find the one that's closest or farthest away from rounding, say, whatever. That's it. Are we good with those? So it doesn't matter how icky, yucky the chemical formula looks. It's always the same, right? A little bit more number crunching, but that's it. Thanks, Peter. Okay, should we try empirical formulas? Who wants to know? Yeah? Okay. Exercises on the back of the front page. Which one do you want to do? So here we're given percent compositions, right? The empirical formula, yep. So which one or ones should we do? Find the yuckiest one.
Does 10 have 3? Does some of those have 3?
Yep. 10 has 3 of them. Let's do 10.
Alright.
10 on the worksheet, part A. So we have 60% carbon, 13.3% hydrogen. Thanks, Tommy. 26.7%, you two, oxygen. What's our first step? Yeah, just, how do we do that? Just change it to grams, right? Because it's out of 100. If we just say we have 100 grams of substance, we're fine, right? All right, now we got to do what? Yeah. Yeah, convert to moles by dividing the molar mass. That's right. 12 grams of carbon to 1 mole of carbon. 1 gram of hydrogen to 1 mole of hydrogen. And 16 grams of oxygen to 1 mole of oxygen. And we can see grams goes away. 60 divided 12 is 5 moles of carbon, 13.3 moles of hydrogen. You all following me? And 26.7 divided 16. I can't do that one in my head. What is it? 1.667. And this one, I didn't round. So I says leave 3 decimal places. I didn't round that.
I rounded that wrong. 1.6.
1 point what?
67.
No, let's have 3 decimal places. That's good. 1.667.
Yeah.
Is that right? Yeah, so yeah, try to have 3 decimal places. So if you want, you can add the zeros, no big deal, but that doesn't really do anything, right? Okay? All right, what's our next step?
Try to find, so they're all whole numbers?
They're not all whole numbers.
Oh,
Only one of them is.
the 5.
Yeah. So we're not there yet. So what do we do, Parker?
Going back real quick, it's 1.669. I'm sorry.
669?
Yeah.
Okay, good.
And then you can divide it all like that.
All of them by 1.669? Why is that? Because that's the smallest. That's right. That's it. Divide all of them by 1.669. And we get 1 for oxygen. What do we get? 5. What's 5 divided 1.669? 2.9958. What's that? That's basically 3, right? Rounds to 3. And what about 13.3 divided 1.669?
That's gonna be 7.9, so we'll just round it to 8.
Is it 7.9? That's it?
It's 7.968.
So basically 8, right? So yeah, we do round a little bit because why? The masses are rounded, right?
Yeah.
But if we don't round too much, I think we're fine. So what's the empirical formula going to be? Someone tell me.
C3H8O.
That's it. Can we do these? Not too bad, right? Are we good with empirical formulas? Do you want to try a molecular formula? Okay. Next side, part. Oh, there's a. So a part B, you're not given the percent composition, but you can still do it, right? Because that one you don't have to change percent to grams. You just use the grams, right? Yeah, go ahead.
You know how we just rounded all those to 3 to 8 and 1?
Uh-huh.
On one of the
Which one?
One of our examples, we got 3.5.
Yeah, and we didn't round that one
Why didn't we round that one?
because that one's not even
Not
close.
even close. So if it's not even
Yeah,
close,
yeah. So
then-
this 3 was 2.999. It's like, oh, that's basically 3. If we owe somebody $2.999 or whatever, we're just gonna give them $3, right?
Would you round down if it was, you wouldn't round down ever, right?
Oh yeah, it could be 2.0001. That's fine, and we'll just say it's 2. So yeah, good question. Good question. So if it's really close, I mean really close, then we're just gonna say, okay, yeah, that's just a rounding error, and so we'll just round it. Because is this really 12? Is this really 1? Is this really 16? No, these are rounded. These are rounded also. So, yeah, and we will always have that issue. So, good question. All right, let's go to section C, back to the second page. Determine the molecular formula of each compound with the given empirical formula and the given molecular weight. When it says molecular weight, that's the same thing as molar mass, right? I don't like using the word molecular weight because weight and mass are not the same thing. But that's me. Every other chemistry book's going to call it molecular weight for some reason. Okay. Just so you know. All right, which one do you want to do on part C?
4.
Number 4? So the empirical formula of this compound is Na2SiO3. And the molecular weight is 732.6 grams per mole. Okay, so what do we got to do? That's it. Get the molar mass of the empirical formula. For sodium is 23. I might be guessing wrong. So is it 23? 23 times 2, that's 46, right? Silicon, what's that? I don't know that one. 28. And oxygen is 16 times 3, that's 48. So this has a molar mass of 80, 94, 102, 122. Did I do my math right? So 122 grams per mole. Okay, so now what do we do?
The weight divided by the number.
Yeah, 732.6 divided by 122, and what is that? 6.0049. So basically 6. Perfect. Okay, so what is that? Is that our answer? No, that is our multiplier. So we multiply this by 6. Thanks, Kai. And we get Na what? 12 Si 6O18. Easy enough? And then section D on the worksheet. You have to find the empirical formula first, right? So those are the big kahunas, right? You got to do everything. Good? Questions? We feel confident? Okay, what should you do?
Go home and practice.
Go home and practice it. That's why I gave you this worksheet, because it's easy to practice, easy to check to see if you did it right. And they are posted on the modules right now. So, sorry I've been a little late on some of the other items, but okay. Hope